two types of matrices that you need to keep track of. This is your input for OmicLoupe. First, you have the design matrix, which consists of the information about your samples. So you have one column with your sample names, and then you have one or multiple columns with different conditions for the samples, so which biological group or different technical conditions. So, and the sample names you have, they should exactly match to columns in your data matrix. So this is how OmicLoupe knows which of these sample entries matches to the data matrix. And so your data matrix, this is where you have the measured values. And so in this case, so you will have these columns representing measurements for samples. And then you have the rows, which in this case represent different proteins, but it can be transcripts or metabolites or something else. And so for each row here, we have multiple measurements for the same protein in different samples. And each sample here consists, each column consists all the measurement for the sample. And so in addition, we can have annotation columns, which consist general annotation information for these proteins. And this can be protein IDs or other things. And you can have any number of these annotation columns. And finally, we have the statistical columns. And so I will show you more in the next slide. So when you do statistical tests, so often you end up doing one test here per, in this case, proteins. And what I've illustrated here is just one of these tests. So we have 12 measurements here of one protein across 12 samples coming from 4 different conditions. And so for each comparison we do, we need, or for each protein, we need to have the average expression level. We need to have, so the log fold change, that's the difference between the groups that we're comparing. In this case, we're comparing the blue group and the green group. And this comparison will give you a p-value, and then when you do this kind of testing, you need to adjust for the many tests that you do, and then you will get an FTR rates. And this is something you do globally. When you have all your p-values, then you can calculate all these adjusted p-values. So to include this in OmicLoupe, you can have one or you can have multiple statistical comparisons. You can also run it without, but then you can only access the plots that doesn't depend on this. So you have the base name here, contrast name. In this case, it's called comp. We see comp is the starting part in each of these 4 columns, and then you need a different ending. And in this case, so we have this average expression, AVEXPER. We have the log FC, and we have the p-value and the add p-value. And this can be specified within OmicLoupe, but if you use this default format, then OmicLoupe will understand it with no additions. And so finally, if you want to give multiple data matrices to OmicLoupe, you need a column that is shared or have shared IDs between these. Otherwise, OmicLoupe will not know which entry matches to which entry. So in this case, we have gene symbols, and also here in the second one in RNA-seq, we have a column, it's called IDX, but this is also gene symbols. So these contain the same types of IDs. And this is only required if you want to use multiple datasets when you run OmicLoupe. So to recap, you have first the design matrix and the data matrix, where the design matrix contains information about your samples and different conditions for these samples. And one column here needs to exactly match the columns that you have in your data matrix. And then in addition to the sample columns, you can have annotations and you can have statistical contrast. And as we talked about the statistical contrast, you need these 4 columns for each comparison you do. You can have multiple, but then you need these 4 columns for each. And then finally, if you want to coordinate different datasets, you need one column that is in common, so OmicLoupe can understand this. And I will show you how to do this in the next video. Thank you.